Discussing about the gravitational potential at a point. The gravitational potential at a point in a gravitational field is defined as the work done per unit mass in bringing that mass from infinity to that point. So, gravitational potential is work done per unit mass. The work done is a scalar, mass is a scalar quantity, so gravitational potential is scalar, and its units are, as work has got the units of joules and mass kgs, that means it has got the units of joule per kg. Now, the dimensions. The dimensions of potential will be, work has got the dimensions of ml2t minus 2, and mass has got the dimensions of m and m gets cancelled, so the dimensions of potential are l2t minus 2. So I will repeat it once again. The gravitational potential at a point in gravitational field is the work done per unit mass in bringing that mass from infinity to that point. Let us calculate the expression for the potential or the gravitational potential at a point. This is the Earth. The Earth is here taken as a perfect sphere of radius r with center O. Let a point A be at a distance x from the center. We have to calculate what is the potential at P. That P is at a distance of r from the center. We will see what is the work done in bringing a mass from A to B. That means from A to B along a distance of dx. When a unit mass m0 is brought from A to B for a short distance dx, we will see what is the work done. That small amount of work done needs to be integrated from infinity to r to get the potential at P. Now, the force, the gravitational force on point mass m0 will be equal to g m0 divided by x square. As m0 is equal to 1 kg, that is unit mass, so F is equal to gm divided by x square. Now, small amount of work done to bring a body from A to B by a small distance dx will be equal to dw, that will be equal to f dx, that will be equal to gm by x square into dx. So, we know that gravitational potential at a point P will be the total amount of work done in bringing a body from infinity to that point. That means we need to integrate, in order to calculate the potential at the P, we need to integrate this dw from infinity to r, because this point P is at a distance of r from the center. So, potential at a point P will be equal to integral of dw from infinity to r, that is integral of infinity to r gm by x square dx. So this integral and this sign goes. So Vp is equal to gm is a constant, so it is taken out of the integral sign. 1 by integral of 1 by x square is equal to minus 1 by x from infinity to r. That means minus gm 1 by x infinity to r. Giving the limits, we get minus gm 1 by r minus 1 by infinity. Firstly, the upper limit, then the lower limit. 1 by infinity is equal to 0, so potential is equal to minus gm by r. So potential at a point P is equal to minus gm by r. If we have to calculate the potential at the surface the radius is r, so at the surface the potential is minus gm by r. Now here this is important, that is, why is it negative? It is negative because the gravitational force is an attractive type of force, so work is done by the field. When the work is done by the field, the potential is negative. When the work is done against the field, the potential is positive. That means a ball does not need to be brought to the earth. It just needs to be left. The earth brings it by the gravitational force of attraction. That means the potential at any point in the gravitational field of Earth is negative. Why is it negative? Because the force is attractive. Work is done by the Earth. Work is not done against the field. Work is done by the field. When the work is done by the field, the potential is negative. When work is done against the field, the potential is positive. Thank you.